Good morning. Today we'll be discussing again a very basic topic in cardiology, and that is the cardiac cycle. So again, I'm Dr. Efren Vicaldo, your lecturer for cardiology. So this is the cardiac cycle, right? So you would note some tracings in here. For instance, the red one is that of the aortic pressure tracing. The blue one is the LV pressure tracing, okay? These are your jugular venous tracing, okay? On the left side, you also have the left atrial pressure. These are your complexes on the electrocardiogram, and these are your heart sounds. So the cardiac cycle defines for us the events that occur from the beginning of one heartbeat to the beginning of the next. And this is what encompasses one cardiac cycle, right? So this involves a series of events. As I mentioned a while ago, you have pressure changes in the chambers and in the great vessels, specifically that of the aorta. You have the valve movements, since we are talking more of the left ventricle, that of the mitral valve and the aortic valve, okay? The electrical events, which would be seen on the surface electrocardiogram. The heart sounds, which is are usually demonstrated by your phonocardiogram, as well as the flow of blood and pressure changes in the various chamber and vessels. Again, this is basically what I was talking about. Again, your aortic pressure over here, your ventricular pressure, okay? This is systole and diastole. These are your heart sounds based on your phonocardiogram. These are your jugular venous waves, your ACV, and these are your complexes on the electrocardiogram, okay? So let's go on. And this is a bigger illustration of the aortic pressure, okay? Take note that diastole, these are the pressures, systole over here, and the next diastole. And these are the ventricular pressure. Take note that diastole, it's low. Then at systole, right, it goes up there and goes down again. And for the next diastole over here, okay? So these are your atrial pressure, specifically that of the left atrium. Worthy of note is the fact that basically the pressure inside the left atria or left atrium is quite low. And again, take note that at diastole, the pressure in both the left ventricle and the left atrium are the same. Okay. So this is your phonocardiogram, which would give us the components of the heart sounds. These are your first and second heart sounds, and perhaps some abnormal sounds, which are your gallop sounds, or your S3 and your S4, which are your gallop sounds. Okay. This is your jugular venous pressure. We know that you have your A wave, your C wave, and your V waves for your positive waves. And these, of course, are the ECG tracing with the various complexes of the components of the electrocardiogram. So again, to repeat, this is your aortic pressure, right? Northy abort is the fact that at the peak systole, the LV systolic pressure and the aortic systolic pressure are the same, okay? And the atrial pressure at the diastole, both the left ventricle and the left atrium are the same, and so with this, right? And this is very important, your left ventricular volume, okay? Take note that there are changes in the volume inside the left ventricle at systole and at diastole, right? So the cardiac cycle basically has two major parts. That of diastole, which is the period of relaxation during which the heart fills with blood, and of course your systole, or the period of contraction. Okay, so systole is illustrated in this portion. Okay, and diastole over here, right? And these are the different phases of the cardiac cycle. These are the different phases at systole, and these ones at diastole, right? So during the isobulomic contraction, as illustrated in this red shaded portion, involves the start of QRS complex. On the electrocardiogram here, these are your QRS, okay? And that is the start of ventricular contraction. So if you look at the ventricular pressure tracing, this is the pressure inside the left ventricle that rises or goes up, right? And this particular portion, since the pressure inside the left ventricle exceeds that of the left atrium, then there is closure of the mitral valve, which brings about, if you look at your heart sounds based on the phonocardiogram, would give you the first component, or the mitral valve closure, or the S1, right? So if we look at, say, the volume inside the left ventricle, the left ventricle is contracting already, but the volume inside the left ventricle is still unchanged, okay? So both the mitral and aortic valves are still are rather close. So the aortic pressure continues to drop and reaches its minimum pressure. And that is that particular illustration of the aortic pressure drop, right? And this is followed by the massive contraction of the ventricle, and it somehow distorts the shape of the atrium. And you see some change in your venous wave that inscribes the so-called C wave. Okay. At the end of this phase, the ventricular pressure equals and exceeds the aortic pressure, that is somewhere over here. That is the aortic pressure, and this is the LV pressure, right? So there is a consequent opening of the aortic valve over in this part of the cardiac cycle. Okay. Now, this is now followed by the phase of rapid ejection, right? So what happens during the rapid ejection? As I mentioned, somewhere here is the aortic valve was already opened, and there is rapid ejection of blood from the left ventricle into the aorta, okay? And there is drop in ventricular volume, right? So if this were the volume inside the left ventricle, at this particular rapid ejection phase, you would note that there is a very significant drop in your left ventricular volume, right? And on the left side further, there is atrial filling via the venous pressure. Okay, you have blood coming from the pulmonary veins going back into the left atrium, and at this portion of the cardiac cycle, the mitral valve is still closed. So the pressure inside the left atrium over here, okay, you would note that the slope of your curve is a little upwards. So this represents the gradual rise in the left atrial pressure. Okay. Now, midway in the cycle, the muscle stops contracting and begins to repolarize. So this is part of your repolarization. If this part of the ECG is left ventricular depolarization, in this particular part of the cardiac cycle, this is repolarization. And this is where you inscribe the T wave. So on the ECG, this is your T wave. And you would note that there is a decrease in both the aortic and the ventricular pressures. Okay. Now, at the end of the ejection phase, the ventricular pressure falls below the aortic pressure, and the aortic valve somewhere in this area, ABC, stands for aortic valve closure, which now corresponds to your second heart sound on the phonocardiogram, right? Over here is your second heart sound, right? So next is your isobolomic relaxation, again illustrated on this particular part of the cardiac cycle, wherein the ventricle is at rest, both valves are closed, and if you look at the volume inside the left ventricle, it is flat, meaning the volume is constant, okay? And the atrial pressure, right? If you look at your atrial pressure tracing, there is some rise in your left atrial pressure, okay? Because blood is continuously going into that particular chamber, right? And this particular portion, you see the inscription of your V wave, right? Now, there is momentary backflow of blood, and there is an aortic valve snapping once it closed, and this would result to your dicrotic knots in this particular area, right? And the ventricular pressure rapidly drops, okay? And take note that this is the slope of your ventricular pressure. So there is a sudden drop in your ventricular pressure, okay? And at this particular portion of the cardiac cycle, the mitral valve opens, right? And somehow, at this particular part of the isobolomic relaxation, you would note that repolarization of ventricle is somehow complete. Now, this is followed by the rapid filling phase. Okay, again, this colored part of the cardiac cycle. And it is at this point that the mitral valve opens and blood flows from the left atrium into the ventricle, right? So the ventricular volume, this is again your ventricular volume. Since you have an inrush of blood from the left atrium into the left ventricle, there is an increase in the volume inside the left ventricle, right? And there is somehow some small drop in the aortic pressure as noted over there, okay? Now, the third heart sound here on the phonocardiogram might be heard at the end of this phase, possibly caused by turbulent flow in an early filled chamber. Take note, however, that S3 gallop is not always normal, right? So be wary of a third heart sound or S3 gallop because this could indicate that there might be some degree of diminished compliance of the left ventricle during this phase of the cardiac cycle, right? And take note that the ECG is quite silent, meaning there is no activity if you look at the electrocardiogram. Now the next phase is that of diastasis. And this is the period in the middle of ventricular diastole. Okay. If you look at your left atrial pressure, again here, you would note some increase in both, right? Because you should remember that the diastole, the LV diastolic pressure and the LA pressure are the same, okay? So initially, they would show a slight increase, but later on, the LA pressure will be slightly higher than the left ventricle, this particular part of the cardiac cycle. And there is some steady, slow drop in your aortic pressure. And again, take note that nothing is going on as far as your phonocardiogram. So no abnormal or normal heart sound is noted in this particular phase of the cardiac cycle. Now, near the end of diastasis, the P wave now, take note that over here is the initial part of your P wave. It's now appearing on the ECG, okay, as the atrial myocardium prepares for atrial systole, right? So during atrial systole, over here in the shaded portion again, what happens is the atria on the left atrium and the right atrium on the right begins to contract, and there is a small rise in the atrial and ventricular pressure, right? So atrial and ventricular pressure, you note some rise, no? And the mitral valve open, or rather is open, and the aortic valve is closed at this part, okay? So the aortic pressure gradually drops as the elastic walls of the artery recoil from the previous systolic ballooning, okay? And the ventricle, this maximum volume, and this is your end diastolic. This is your end diastolic volume over here, right? Take note that this is your LV volume curve, right? So again, the ECG over here overlaps the beginning of this phase. And at the latter part, you see the QRS complex, which heralds the next systole, right? And the phonocardiogram is somehow is silent, right? Now let's go into the so-called pressure volume loop. If you recall, again, these are your tracings inside the left ventricle as far as the pressure inside the left ventricle is concerned. These are the corresponding sounds that you would hear as the mitral valve closes, right? The aortic valve opens in this part of the cardiac cycle, the aortic valve closure on that part, and the mitral valve opening on this part of the cardiac cycle. Again, if you correlate the volume inside the left ventricle, as blood gets ejected from the left ventricle into the aorta, you would note that there is a significant drop in your LV volume during systole, only for it to fill again during diastole. This is an illustration of your pressure volume curve. Take note that on your x-axis is your LV volume, And over in this axis is your pressure. Okay, so these are the corresponding gradation, and this is in terms of volume. So over here is the phase of isobolomic contraction. No? Take note that pressure goes up, right? But there is no change in your volume. Okay. And over here is the opening of the aortic valve, so that now blood gets out into the aorta, and the volume inside the left ventricle drops. So there is drop in your left ventricular volume, and you reach some peak systolic pressure over here, right? And somewhere in this area, the aortic valve closes, and this is followed by the phase of isobulomic relaxation, meaning there is a drop in your LV pressure without change in your volume, right? And somewhere over here, the mitral valve opens so that the blood again goes from the left atrium into the left ventricle. So there is now a steady increase of blood inside the left ventricle. So this is the normal volume or pressure volume loop in a normal individual as represented accordingly. And take note that over here is your so-called end-diastolic volume, and this is your end-systolic volume, meaning the volume inside the left ventricle at end diastole. This is the volume inside the left ventricle at end systole. If you subtract the value representing your end diastolic volume, subtract your end systolic volume from end diastolic volume, then you get your stroke volume, right? If you divide the EDV or end diastolic volume by your stroke volume, you get your so-called ejection fraction. These are significant because this could somehow give us an idea as to how good or how bad the left ventricle is performing. This is an illustration of pressure volume loop in patients with left ventricular systolic dysfunction, or simply put, patients with congestive heart failure. Take note that if we use this as our reference volume loop, right? In patients with congestive heart failure, this is what happens in the pressure volume loop. And since there is diminished contractility or inotropic state of the left ventricle, this would result to a lower stroke volume. Take note that the stroke volume is this volume minus this volume. So the stroke volume only becomes this much, no? Stroke volume, and that is the stroke volume rather is lower than the reference stroke volume in normal individuals, right? And if you may take note, the pressure inside the left ventricle is also slightly higher, and your peak systolic pressure is kind of lower compared to that of the normal. Okay. Now this is a pressure volume loop in patients with diastolic dysfunction. What is a good example of patients with left ventricular diastolic dysfunction? This is commonly seen in patients, for instance, with uncontrolled hypertension, wherein the left ventricle undergoes some form of concentric remodeling or concentric hypertrophy, so that this would now give us an abnormal or different configuration of your pressure volume loop. If you again recall, this is our reference normal, okay, or control loop, right? And this is our pressure volume loop in patients with left ventricular diastolic dysfunction. You would note that if you look at your pressure inside the left ventricle, okay, If this is the normal EDP or diastolic pressure, in patients with, say, LV dysfunction, the diastolic pressure is elevated. And take note that, again, the stroke volume, if this were the reference stroke volume for normal people, then this becomes the stroke volume for patients with LV dysfunction. So the stroke volume is expected to be lower than normal in patients with LV dysfunction. And again, your peak systolic pressure over here, if it were normal, if it were those with LV dysfunction, diastolic at that, would have a lower peak systolic pressure. This is the PV loop of a patient with left ventricular outflow obstruction, exemplified by valvular heart disease such as aortic stenosis. What happens in aortic stenosis is, since you have an outflow tract, meaning the aortic valve is narrow, then the left ventricle has to generate a great intracavitary pressure to overcome that obstruction, to come up with more or less a close to normal stroke volume or ejection fraction. So what is characteristic of patients with aortic stenosis is your peak systolic pressure. Again, if this were the peak systolic pressure of normal or controlled group, meaning people without aortic stenosis, this is the peak systolic pressure elevated in patients with aortic stenosis. And what happens to the stroke volume? Okay, your end diastolic volume minus your end systolic volume, if it were normal, would be this. But your stroke volume in patients with aortic stenosis would be lower, right? So stroke volume would be low, and your end systolic volume would be elevated. This is your normal and systolic volume. This is the end systolic volume of patients with aortic stenosis, which is elevated. What about in patients with AR or aortic regurgitation? What is the problem in patients with AR, right? So in AR, this is characterized by an increase in preload. Why? Because inside the left ventricle, you have blood returning to it, both from the left atrium and the regurgitant volume from the aorta because of your incompetent aortic valve. So preload is increased, so therefore your end diastolic volume is way increased compared to the reference normal, right? And the reason for that, as I've said, is because of your usual or normal venous return from the left atrium plus the regurgitant volume from the aortic valve. The peak systolic pressure, these were normal. In AR, this is elevated because of the significant volume being ejected because of an increased preload, right? So consequently, your stroke volume would be increased. This is the stroke volume that would be higher. And so with your so-called ejection fraction, no, would also be higher than normal. Now this is your pressure volume loop in another valvular heart disease. This time, this is your mitral valve stenosis. So what is the hemodynamics of mitral stenosis? You have an obstruction to left ventricular inflow, so that the volume inside the left ventricle is significantly lower because of that obstruction, meaning the LV is underfilled. So that the so-called end diastolic volume, right? If this were the normal end diastolic volume, in mitral stenosis, it would be lower, no? Going towards the left, so lower end diastolic volume. And if you try to reference it with the normal, from here to there would be your stroke volume normal. In patients with mitral stenosis, the stroke volume would be significantly lower, right? Now over here is the pressure volume loop in patients again with valvular heart disease, your mitral valve regurgitation, okay? And what happens here is, again, if you use this as your reference normal from here to there, that is your stroke volume. In patients with mitral regurgitation, the stroke volume is increased, right? Okay. Again, because of an increased volume inside the left ventricle, right? So then diastolic volume, if it were normal only here, then it is increased, right? So the ejection fraction towards the aorta is actually lower because part of the volume being ejected from the left ventricle goes two ways, no? Into the aorta and the other one back into the left atrium. So basically, that ends my lecture for this morning, and I thank you for your attention.